All right, hi everybody. Welcome to our ninth class of electromagnetism. So yeah, we're just gonna start with homework review. So next slide. Yeah, so this first problem is like kind of like a trick problem. It's like very useful technique for advanced electromagnetism also. And this is like a simple case of it. So we have like a 12-volt batteries and we have six farad capacitors. And to find the charge on capacitor C, we apply the voltage loop rule. So we take this loop that I drew here in red, and you see that this loop that I drew, it only has this battery and this capacitor. So and now because of the voltage loop rule, we just have that V minus QC equals 0. Therefore, the charge in the capacitor is just V over C equals 2 coulombs. Does everybody get that? Any questions? Okay, yeah. Next slide then. So this problem is actually an AP problem. So what we're doing is that we're putting the switch to position A, and we want to find the Q on capacitor 1 as a function of time. So to do this, we again, voltage loop rule, epsilon minus I R for resistor 1 minus Q as a function of time over C for the capacitor, the voltage across the capacitor, minus I R for the voltage across the resistor 2, and this equals 0. And you can solve this with you can use I equals dq dt, solve this differential equation. I won't do that right now. Or you can like remember the result we got last class. The result we actually got was um Q equals epsilon times the capacitance times 1 minus e to the negative t over RC, except in this case R is 2R. The equivalent resistance is 2R because these resistors are in series. So you can say that R plus R is 2R. So this is our function for Q as a function of time. Any questions? Next slide then. Yeah, so now in parts B and C, we're basically this is for a long time. It's been at position A, and now we're switching to position B. So what is the direction of the current? So to tackle like these types of problems, just think about what happens to the charge in the first case. So in the first case, we have like this side of the battery is plus and this side of the battery is minus. So after a long time, all the charge that accumulates on the capacitor will be like there will be a positive charge on this plate and a negative charge on this plate. Therefore, when we put the switch to position B and we just have this loop, then the current's gonna run from the positive end to the negative end, right? That's our convention. So it's gonna run like that clockwise. So then the direction of the current through resistor 1 is going to be up. And then they're asking us to determine an expression for, let me just erase this. They're asking us to determine an expression for the charge on the positive plate of capacitor 2 a long time after. So note that they told us that the total charge on capacitor 1 is Q naught at the beginning, like when we close uh switch B, it's Q naught and this is 0. So after a long time, this charge will evenly distribute throughout the capacitors. So we simply have that the charge on capacitor 2 is Q naught over 2. This also arises from the voltage loop rule because we have Q naught, or we have, let me erase that. We can say that the Q on capacitor 1 over C is the voltage across capacitor 1 minus Q2 over C is the voltage across 2 equals 0. But we also have that like conservation of charge. We just have that Q1 plus Q2 is actually Q naught. So if you solve this, you simply get Q naught over 2 is both Q1 and Q2. All right, yeah. Any questions on parts B and C? If not, you can move to the next slide. All right, yeah. So here we have a solenoid with the given inductance and a resistor with the given resistance. And you want to find the time to reach 80% of the final value. Does anybody want to like share their solution to this if you want? All right, that's fine. Remember the time constant tau L equals L over R. This is very important for finding like the when the current's going to reach a certain percentage of its initial value. Because we know that the current for an RL circuit equals um we know that the current for an RL circuit equals epsilon times 1 minus e to the negative t RT over L, right? So I should probably write that. V over R. V over R minus 1 minus e to the negative RT over L. So we want when I is 80%. So we simply say that 1 minus the in the current at time t has to be 8 tenths times the value at time is 0. But when time is 0, the current is proportional to 1. So we can solve this. You can plug in the numbers. These numbers you can plug in. Also remember kilo ohm micro henries. Those are important. And yeah, you can get the answer for T. Are there any questions about that? Oh, and there's also part B. What is the current through the resistor at time T equals 1 time constant? So at 1 time constant, you'll have that I equals V over R times 1 minus e to the negative t over tau. So when t is just tau, this becomes 1. And you can plug in V, you can plug in R, and you can get the answer for the current. Any questions about question 3? All right, if not, we can move on to the actual concepts for today. So next slide. Yeah. So we have LC, or yeah, so we have LC, RLC, and AC circuits. So we'll begin with LC circuits. So let me clear. So LC circuits, so we covered RL and we covered RC. RL was a resistor inductor, RC is a resistor capacitor. Now here we can combine the L and the C for an LC circuit with an inductor and a capacitor. And LC circuits do not have battery because the current will like flow without a electromotive force. But we will see later, but that the current is not constant. the current flows forever, but it is not constant. It'll it'll be like a sinusoid. It'll vary up and like it'll vary. And we'll also see that it's kind of like a cycle. The capacitor will discharge, it'll recharge. And yeah, to solve for this, as we solve for the RL and RC circuits, we just use voltage loop rules. So next slide. So we want to find the function for the charge on the capacitor as a function of time for a LC circuit. Sorry, that's a mistypo. So I'll give you some time to think about this, and then I'll go through it. Just remember voltage loop rule. That's like gonna be the most important thing. Okay, I think I'll go through this right now. Was anybody able to do it? If so, do you want to like share your solution? That's fine. I'll just go through it. So remember that the voltage across an inductor is L di dt, and the voltage across the capacitor is Q over C. So voltage loop rule, VL plus VC equals 0. So L times di dt plus Q over C equals 0. And remember that I equals dq dt. So we have L times d squared q dt squared, like the second derivative of the function of the charge, and the function over c equals 0. So you can solve this um, second order differential equation, and you will get a cosine function. And this is representative of the physical system. We'll see that later. So next slide. Yeah, so the cosine function you actually get is q of t equals q naught times cosine omega t plus phi. So q naught will be like the maximum charge that capacitor has as the LC circuit like keeps on oscillating kind of. So if we started with a charge of q naught and there's no current, like let's say there's like a switch and then we flip the switch, then if this is positive and negative, we would just get a current flowing, and then this current would oscillate. You can see that I equals dq dt, which equals negative omega q naught sine omega t plus phi. And one thing I think I forgot to know is that omega equals square root of 1 over LC. This is just from the math that you solve. And this is the angular frequency of the oscillation. And yeah, that's basically it. And you can also see that you see we have the current and the charge as a function of time. And if you plug in t equals 0, we see that the charge is going to be q naught and the current is actually going to be 0. Which makes sense, which is what I just said previously, that at time 0 we have our fully charged capacitor without any current. And this phase, this is the phi symbol, it stands in for phase. This is kind of like just like an offset of um the charge. You don't need to worry about it very much. That's just there in the expression. Yeah. All right. So yeah, so an LC circuit, yeah, as I just discussed, it has these sinusoidal oscillations. And yeah, it'll oscillate forever. As you'll see, in a couple of minutes, it can actually it won't oscillate forever if you add a resistor. But anyway, so you can see here. So this is what I described at time t equals 0. You have Q naught, a positive and a negative Q naught on both plates of the capacitor, and the current is 0. And then if you like turn it on, then the Q naught, well, there'll be a current going through this because of the positive and negative, right? You have this current, and eventually it'll be such that Q equals zero. And you from your cosine and from your cosine uh function, you actually see that this happens at time t equals big T over 4, where big T is like the total period, the total time it takes to come back to this state again, the period of the oscillation. So anyways, so from this step, then the will become zero, and the charge will flip. Now this side will be negative and this side will be positive. And then and then we'll get a because of this we'll get a current going clockwise because it goes from positive to negative. So we'll get this current, and eventually Q equals zero again at 3T over 4. And yeah, that's kind of like physically what happens in the LC circuit. So are there any questions about that? If not, yeah, can move on. And one last thing is the energy in an LC circuit. So we have that the energy is given by Q squared over 2C for a capacitor. That's just something we know. And for the inductor, it's 1/2 Li squared, if you remember from previous classes. So we can also like model this instead of like current and charge, we can also say that the energy is switching from being stored in the electrical field of the capacitor and being stored in the magnetic field of the inductor. Because when the capacitor is charged, it has an electric field and you're storing electrical field energy in that. But when the charge on the capacitor is zero, your inductor will have a magnetic field which stores that energy kind of. So, like by conservation of energy, we can say that Q squared over 2C plus 1/2 Li squared equals zero. And this will also actually lead to an expression for Q as a function of time. Uh, if you plug in I equals dq dt and you can solve accordingly. And yeah, are there any questions about that? If not, we can move on then.
Wait, yeah, let's talk a bit about RLC circuits now. Right, so when we talk about an RLC circuit right now, let's investigate when we have a capacitor and a resistor and an inductor in series, right? In general, RLC circuits, it's just any combination of resistor, capacitor, and inductor, but this will be the simplest case that we'll be studying. Uh, so notice how we have a resistor here, right? So a resistor, how it works is basically, like when a current goes through it, the resistor, it turns in the electrical energy into thermal energy, right? And if originally when we first studied circuits, we studied like we have a battery and then you got a resistor, right? And then you got, yeah, it's just a battery and a resistor in series. You have the resistor that's it's emitting thermal energy because current is traveling through it. And then you have the battery that's converting its like chemical potential energy into electrical energy, right? Now electrical energy is converted into thermal energy by the resistor. So that means that like, we have a constant current over time because there's no um like the overall electrical energy stays constant. It's just like you have the battery providing the chemical energy that turns into electrical energy, and at the same time, you have a resistor that's releasing energy from the circuit. But this RLC circuit that we're studying here, so it just has a inductor, a resistor, and a capacitor, right? There's no battery, meaning that uh the resistor it serves as like an element that dissipates heat from the circuit. So you don't have any element that's putting energy into the circuit. You only have element that is releasing energy from the circuit, meaning that the total electromagnetic energy it decreases over time, and that's because of the resistor over here. And it's mechanically equivalent to a damped spring or damped pendulum. And I'll show you later why that is so. All right, and then if we're looking at the energy stored, okay, that'll be the energy in the inductor, which is Li squared over 2, and then the energy in the capacitor, which is Q squared over 2C, right? And if we're looking at the change in energy over time, you know that the power, so the power of the resistor, right? That's just the change in energy divided by change in time, right? For a resistor, that's I squared R. We learned that when we were doing, remember we said that, like, you have power equals to I times V, and you use Ohm's law to turn into I squared R, right? And then how are we getting Li times di over dt plus Q over C plus dQ over dt? Well, that's because we're just doing, we're just taking the derivative of the energy over time, right? So this is just like an energy equation that you can get when you're looking at an RLC circuit. Let's go on. Oh, wait, hold on. Yeah, so analogy between RLC and a damped spring. Uh, yeah, so right now, let's look at the differential equation you can write when you're solving an RLC circuit, right? So you know your Kirchhoff loop rule, right? So you uh have a voltage drop here, right? You also have a voltage drop here. And so we can say that there is like the sum of the total like voltage drop and voltage rise, right? That has to equal to zero. So our differential equation, right, that will equal to something like uh okay, so across the resistor, right, it will be it's basically I times R, right? So I times R, and then across the capacitor, it's Q over C, right? So I over R plus Q over C. That'll be the total voltage drop across the resistor and the capacitor, right? But then we also have a voltage rise across the inductor, right? So we're gonna say uh equals to our uh Li dot, right? Li dot. Now, okay, we can also say that because the capacitor originally, for example, the capacitor originally had charge, right? And then we're losing energy in the circuit, so that charge is like it's gonna be discharging, right? The capacitor is gonna discharge, so we can say that like the charge on the capacitor is decreasing, so Q dot is less than zero, but we know that the current is positive, right? So we'll say Q dot that equals to the negative current, right? Uh, right, yeah. Okay, yeah, and then we can plug that in, right? So we should be getting, hmm, let's see. Oh, yeah, okay. So we'll just say like negative. Oh, all right. Let me erase this. I drew this wrong. Q dot is negative current, right? So negative Q dot R plus Q over C, right? Uh, yeah, Q over C should equal to the sheet. All right, let's say plus this equals to zero, right? Uh, if it were charging, then we have the differential equation that's LQ double dot, right? That equals to zero. That's the differential equation you have over here, right? Uh, but what it actually is, right? So, if we look at the something over here, like a damped spring, right? So, for example, let's look at the mechanical one. So we have a spring, it's attached to a mass. All right, so we have m x double dot, right? That's our acceleration equals to negative kx, right? And then how can we have a damping term? Well, you know that if you want to have a damping term, right? So, example, let's say this is the equilibrium position, right? You know your force will be pointing your F spring, right? So this will be negative kx term because that's just restoring, right? And then, for example, if the mass is moving in this direction, right? So it's moving towards the left. Then if you want a damping term, right? You want the force to be in the opposite direction of the velocity. So it will be like, for example, some v times the velocity. And we pointing towards the right, right? So it'll be in the opposite direction of the velocity. So minus b times the velocity, right? We can also write velocity as x dot. This is just the derivative of x with respect to time, right? So we're getting mx double dot plus kx plus dx dot, right? And you can see that equals to 0, right? And that's equivalent to our differential equation over here. We're getting is QR plus Q over C plus L cubed double dot equals to 0. They're both second order differential equations, and then both have a damping term, right? The damping term here is this one over here, the Q dot R. That's just the I times the R, and it's just like you have energy dissipated because of yeah. Does that make sense, everyone? If you guys have any questions, just like message me in the chat, and I'll be more than happy to go over it. Yeah, let's go on. All right, here's the problem. I sort of gave you a hint already. Solve for the charge and current as a function of time in this RLC circuit. So remember, set up your differential equation for like the Kirchhoff loop rule. So remember the sum of the like if you have a voltage drop and you have voltage rise over entire loop, you know it has to equal to 0, right? So remember sigma of all the voltages across the loop equals to 0. So give you guys some time to do this and we'll go over it. Yeah. maybe like 1 or 2 minutes, and then we'll go over it. All right, let's go over this. This part will contain a bit of math because it involves solving some differential equation, but let's first write the circuit differential equation, right? So we have draw across capacitor, right? So Q over C, and then cross inductor, we plus L times your I dot is a di over dt, right? And then plus your IR, right? IR, that has to equal to 0. Now, okay, let's say right now, right? Right, okay, so right now, it's a damped circuit, right? So I'll say that Q dot would equal to my current. So I can change my differential equation into, instead of this, it will be just a safe space. I'll change it into, so Q over C is still there, Q over C, and then for the current, right, it's Q dot times R, and then Li dot would be L times Q double dot, right? L times Q double dot, that equals to 0. And now I want to solve for the charge as a function of time, right? Now to do that, it's a bit complicated. So let's first examine, like, in general, if I have a differential equation that looks like, for example, x double dot, and then right now I'll say plus 2 gamma x dot. You'll see why I do 2 gamma. It will just make things look nicer. And then plus, like, for example, let's say alpha, okay? Alpha x and then plus beta, okay? That equals to 0. How do I solve this? Well, so this is a bit like sort of cheating, but I'd say that I'll guess a solution x equals to a times e to the alpha t, and then you'll see that it turns out to be the correct solution. But like it's a bit like once you know the solution, you know this is correct, right? But I'm telling you that if you guess, like, if you plug in x equals a times e to the alpha t, right? Then you will get a correct answer, okay? So if I plug in x equals a times e to alpha t, then what I'll get is, okay, when I do x double dot, I'll get alpha squared and then times alpha squared and then times x, right? Because once you take the you can take the derivative of this, right? Second derivative of that, so alpha squared times x, and then plus 2 gamma x dot, right? So 2 gamma alpha, and then once you do it, you'll find it's another x, right? And then times alpha x. Oh shoot, okay, my bad. I use, like, I don't want to confuse the variables, so call this e to the omega t. Uh, wait, how about I'll call it e to the 5. I don't want to confuse any variables, so let's say e to the uh maybe let's say nt. Okay, just to not confuse the variables, right? So instead be n squared x plus 2 gamma n, right, nx and plus alpha x plus beta. This equals to 0. Right, give me a second. Yeah, yeah, yeah. Yeah, yeah, yeah. Right, okay. And then those all right, so let's say we ignore the constant term for now, so there's no constant term. So let's take away the x because we can just cancel that out. So we can solve like, n squared plus 2 gamma n plus alpha that equals to 0. Well, look, it's just a simple quadratic equation, right? So what's n equal to? We can say n, that equals to, um, so negative 2 gamma plus or minus square root of, wait, 4 gamma squared minus 4 alpha, right? And then divided by 2, right? So what does that equal to? That equals to negative gamma plus or minus plus or minus we can take the 2 out, right? And that cancels. So square root of gamma squared minus alpha. And so what is our final solution? Well, our final solution is x is equal to so some constant a, right? A times e to the gamma t, right? So right, a times wait, in general, it will be like because we have two different solutions for n, right? And have negative gamma plus square root of gamma squared minus alpha, or negative gamma minus square root of gamma squared minus alpha, right? So we can say it's a e to the first n, right? So it will be a e to the or we can let's say we pull out the negative gamma first. So say x is equal to e to the negative gamma t. By the way, if you guys don't get this, is okay because it's just a bunch of math and you just need to know the results, right? So a e to the square root of gamma squared minus alpha and times t. Let me draw a divider so you guys don't get it mixed up. All right. And then, so plus some other constant b times e to the negative square root of gamma squared minus alpha, right? Negative square root of gamma squared minus alpha t. This is your general solution. How are you going to get A and B? Well, you get it from initial conditions, right? So, okay, we've gotten like, this was our original, oh, wait, no, that was not. Uh, this was our original, let me draw a square. This was our, right, this was our original differential equation, and this will be our solution, right? Okay, so now that we know this result, right, we can go back over here. So what we'll get is, okay, if I divide the L over, so divide by L, divide by L, okay, then what I'll get is that Q as a function of time, Q as a function of time, will that be equal to? Well, first, e to the negative gamma t, right? So e to the negative gamma t. What is gamma here? Gamma is r over 2l, right? Because this term over here, 2 gamma over here, matches with, let me change the color so you guys can see it better. Uh, and we have this 2 gamma over here that matches with this over here because you can think of x as my cube, right? So e to the negative r over 2l negative, right, r negative r divided by 2l, and then we'll be inside will be sum a times e to the gamma squared minus alpha, right? What's my alpha here? Or remember, my alpha it matched with my alpha matched with the this term over here. So my alpha will be 1 over LC, right? So e to the square root of gamma squared minus alpha, right? So let me go over here. What's gamma squared minus alpha? Gamma squared minus alpha, that'll be equal to r over 2l squared over 2l squared, and then minus my alpha, which would be 1 over LC, right? So let's say I, I'll do square root of this, square root of this, right? And let's call it big omega for now. We can plug it in later, right? So then my solution would just be a to the big omega t uh plus b times e to the negative big omega t, right? This is our final solution for the charge as a function of time. And so you can see it's all in terms of the resistance, the capacitance, and the inductance, right? We have omega over here, and omega is just this quantity over here. So it's just this over here. And that'll be your final solution for your charge. How you're going to get A and B will be getting from the initial conditions. So you can put like, for example, t equals 0, and you can solve for A and B, right? Uh, yeah. Right, that should yeah, that's our charge as a function of time. If you want to find current as a function of time, well, you know that I equals to your q dot, right? So dq over dt. So all you have to do is just take the derivative of this with respect to time, and you can get your current as a function of time. I'm not going to do that now because it's just a bunch of more math, but you get the idea. So basically overall, just like write your second order differential equation. It'll just be this over here. And once you do that, if you know the general solution for this type of second order differential equation, you can immediately go and find your charge as a function of time. And then to find like the two constants over here, you plug in initial conditions and you can solve for both of them. Yeah, I know this was a lot. So if you have any questions, just let me know in the chat. But let's quickly move on for now. Let's clear that. All right, let's go on to AC circuits. Hopefully this will be a bit better. AC, okay, that means alternating current. Because we have an alternating current, we also have an alternating oscillating voltage. So alternating current or like oscillating voltage, what we do is we represent each of them as complex exponential functions. Basically, we can say like I, and usually for AC, we'll put like that curly thing on top. So I equal to some, I zero e to the like I times, for example, omega t, and then plus like some phase shift for the I, right? And similarly, we'll say that uh V, the complex voltage will be equal to like some V zero, right? And times e to the I times omega t, and then plus some other phase angle for voltage. Why do we care about the phase angle? Well, because basically once I had these two complex exponentials, uh you can think of these as like, for example, I have a circle, and then for the current case, we'll have radius I, right? And then I'll think of the current as like a rotating vector, right? Because the current it will be rotating at a speed of omega, or angular velocity of omega, right? And then the initial angle when t equals 0 would be phi I, right? And then this vector, it will have a constant length of I0, right? That's why I express it as a complex exponential. You'll see how that gets useful later. But from these complex exponentials, you'll see that we only care about the real component because that's the only part that has physical meaning. So we'll say that current I as a function of time, right, as like for example, I0 and then times like cosine. So cosine of, and then what's in here, right? So omega t plus phi I. And we can do a similar thing for the voltage, right? So voltage will just be V0 times cosine omega t plus phi V, right? But this phi over here is just like, when I have time equals 0, what's the initial state of the current? All right, so for AC circuits, we still have Kirchhoff's loop rule, and the definition of voltage drop across the elements are unchanged. So for example, we still have the voltage across a resistor is equal to the current on the resistor. So IR across and then times like the resistance, right? And we also have, for example, VL equals to like LI dot and so on. We also have like VC equals Q over C. And yeah, so Kirchhoff's loop rule and like how you define voltage drop across the elements, a lot of that is unchanged even when we're looking at AC circuits. Uh, now let's go on. But something that is yeah, so Ohm's law, when we had V equals IR, we used that when we had a DC circuit. And the thing about it is that V equals IR, this only applies for resistors, right? Now, what we want to do is we want to do something called V equals to the current in the AC case, right? And then times what we call the complex impedance. So we'll call the complex impedance Z. Uh, so the thing about this is, it looks pretty similar to V equals IR, right? But V equals IR, that's like only for resistors. What we want to do is we want to say that for any arbitrary element in a circuit in an AC circuit, we want to define its own complex impedance. So we can just directly say that the voltage across that element is equal to the current through that element and times its own complex impedance, Z, right? And you'll find it's simpler than having to solve a differential equation, like actually saying V equals like, for example, for an inductor, V equals Li dot. Let's say it's in an AC case, right? You'll find that if we define like a complex impedance, it will be a lot easier to do some problems. So let's go on to yeah. So I said that each element in the circuit has its own different complex impedance. So let's go on to try to derive what's the complex impedance for different types of elements in the circuit in an AC circuit. So all right, let's first talk about resistors. So remember when we have a resistor, have V equals I times R. Now, in an AC circuit, we still have uh the AC voltage, basically the voltage across it in the AC case, equal to the current through it, which I'll also say is AC, and then times the resistance. Okay, well, I'm also saying that if I define a complex impedance, right, that equals to so the V across the element equals to the current and times the complex impedance of a resistor. And what does this mean? Well, this just means that the complex impedance of a resistor, oops, complex impedance of a resistor, ZR, that just equals to the resistance, right? It's pretty simple. So this is a really trivial case when we're looking at the complex impedance of a resistor. The complex impedance of the resistor is just the resistance. Uh, yeah, so it's a pretty neat way. it's just like for resistors, right? It's a really simple element. You just have this simple relationship between the voltage and the current. So you'd also expect the complex impedance to be really simple, right? I think there's an example problem on this. Let's take a look at that. Yeah, let's do this one first before we derive the complex impedance of some other elements. Uh, Using the complex impedance way, derive an equation for the current as a function of time through the circuit. If I say that the voltage, so this just represents an AC voltage source. So I'll say the voltage in like across like this voltage across the source will equal to like let's say some V0, I'll say E to the I omega T plus 5e. It's really helpful to think of voltage as a complex exponential because this way, you can take derivatives and you'll also find that that is how we're gonna get complex impedances because complex impedance it's like a complex number, right? So we'll express voltage and current as complex numbers. So if we have this V equals V0 e to I omega t plus 5e, okay, then use the complex impedance way that voltage equals to the current, which we want to solve for, and times the complex impedance, right? Z. And just remember that Z, the complex impedance for a resistor, is just equal to its resistance. So I'll maybe give you guys a minute or two to do this because it should be pretty simple and try to solve for the current as a function of time. Okay. We want current as a function of time. All right, let's go over this. Alvin, well, yeah, Alvin, do you have any idea on how to do the problem? You can type in the chat if you want. Okay, yeah, I'll just go over it then. Right, so we have this relationship, right? V equals I times the complex impedance. You know the complex impedance for a resistor is just R, right? So we'll say this equals to the current. So basically current as a function of time, and then times the resistance, right? Well, okay, I already know the voltage, right? It's right over here. So what does this get us? Well, then I'll just say that just equals to voltage divided by resistance, right? So that would just be equal to V0, V0 divided by R. And this time I'll convert the complex exponential to like the real function, right? So times cosine omega t and then plus some phase angle phi v, right? Yeah, so that's just our final answer for the current as a function of time through this AC circuit. Oops. This is just our final answer. You can see it's just as if we have V over R, but except we now have like cosine omega t plus phi v, right? This just serves as the term that shows like how the voltage and also the current it's like oscillating, right? Okay. Yeah, so that's our first problem. Uh, Alan, does that make sense to you? Okay, let's move on and clear these drawings. Okay, let's go to inductors, right? So let's try to derive the complex impedance for an inductor, right? So, okay, oops, this capacitor, let's go here. Hey, you know that voltage, uh, and we're saying voltage equals to the current and then times the complex impedance, right? Right now we're looking at just an inductor. Okay, I also know that it equals to L times di over dt, right? Because that's just the definition of inductor and di over dt, right? L times di over dt, that law still holds. Okay, well, if I say that my, let's say that just equals to I0, I0 e to the I times what, omega t plus phi I, because I know it's an AC circuit, omega t plus phi I. Okay, and then, okay, what happens is I do d over dt, right? So then this just equals to L, and then when I do d over dt, right, I'll get the I omega here. So L times I times omega, and then times I0 e to the I omega t, right? Plus the I omega t, and then plus phi I, right? And then the I0 e to the omega t plus phi I can cancel this out. This is just equal to the current, right? And remember, this should equal to the current times the complex impedance. Well, then we just got the complex impedance of an inductor, right? Complex impedance of an inductor, that's just equal to I omega L. Isn't that cool? And now you can notice that, before my complex impedance for a resistor, right? Remember, complex impedance of a resistor, that was just equal to R. R is just a real number. Now, complex impedance of an inductor, on the other hand, it's I omega L. I omega L is a purely complex number. So let's look at the implications of that, right? Uh, so for example, if I know that this is my I, right? My I is a function of time, well then I'll know that my voltage as a function of time, that's my current, and then times my complex impedance. So it's equal to I0 times omega L and times I times e to the I omega t. Now, if you remember from your like pre-calculus or like algebra 2 or like geometry days, right? If you think of e to the I omega t plus phi as a vector, right? So I'll draw over here. So uh this will be let me switch a color. Let's go over here. So I'll draw a circle here. I'll draw my coordinate system. So this will be my vector it'll be a unit vector representing the current, right? So this I'll say is equal to say I cat vector. Okay. Now this vector, it's rotating, right? Now, if I multiply my I cat vector by an I over here, I'm essentially just rotating it by 90 degrees. So if I rotate it by 90 degrees, right, this is equal to my VT, right? So if I rotate it by 90 degrees, then I can also write this, right? I write this as equal to I0 omega L, and then my complex exponential is still e to the I omega t, but now my phi I has changed, right? It's moved by 90 degrees, also like pi over 2, right? So plus, instead of just phi I, will be phi I. Oh, I'm running out of space here. Say phi I, and then plus pi over 2. Plus pi over 2. And then so this will be my voltage unit vector. And it's also rotating at an angular velocity of omega. So the cool thing is that if you think of your voltage and your current as unit vectors uh, that are rotating in a circle, you'll see that your voltage in like if you have the case where it's just um like right now we're just looking at if you have like an AC source and then you got an inductor, right? That's your inductor. You'll find that the voltage is 90 degrees ahead of the current, right? So in other words, I'll say my current is equal to I0. Now I'm taking the real part, right? So I0 cosine, right? I0 cosine omega t plus like some phi I, right? Now I'm adding 90 degrees to the phi I when I'm doing my V, right? So I'll get V, or I'm gonna say like is equal to V0 and then times I think negative, right, negative V0 sine omega t plus phi I, right? I'm taking the real part, right? So notice that I and V, they're off by 90 degrees in their phase. So I will be going in a cosine function, V will be going in a sine function. So if I also want to graph each of the currents, uh, let's use red, then I'll get, I want to graph, this is as a function of time, right? My time will be this axis, and then so my current is cosine, right? Let's assume that for simplicity, maybe like let's say phi is equal to 0, right? Then my current, the graph of the current, let's draw it in yellow. My current will look something like this, right? This is my graph of current. Also go over there, right? So that's going to be my current. And now my voltage, it's the negative sign, right? So instead, voltage will look something like, voltage would be like, you're trying to draw it well. So you're looking like, right. So it's off by 90 degrees, right? So the purple will be what's my voltage as a function of time. And you can see they're offset by like a certain phase angle, right? You can get the current, or you can get the current by shifting the voltage by 90 degrees, right? And that's because our complex impedance is a complex number, right? Because I'm doing I times omega L. So it's just shifting the voltage from like the voltage can be gotten from shifting the current, right? So this will be our final answer for the currents and the voltages. And overall, this will be our complex impedance. And it's just I omega L. So it's really useful to know this. Just remember we got it from doing like it's equal to voltage is equal to I times the complex impedance, but we also know it's equal to L times di over dt. And then after we like plugged in our current, which we know is like AC, and we can get this will be our complex impedance. So yeah. Uh any questions on that part? If not, let's go on to finding complex impedance of a capacitor, which will be slightly more complicated, but it's a very similar idea. So capacitor. Now we're considering when we have this is our AC source, and then we have the capacitor over here. Okay, I know again, mm, V is equal to my complex V is equal to my complex I and times my complex impedance, right? Say ZC. Now we know for capacitors, right? This equals to Q divided by C. How do I express Q as a function? Like, I want to connect Q and current, right? So I want to find Q in terms of current, right? Well, Q again. How do or current, right? Current is just I equals dq over dt, right? So if I want to find the charge, I just integrate the current over time, right? So this equals to integral of I dt and then divided by the capacitance, right? Now, again, I know that I uh remember we said that I equals to, and we'll say it's equal to I sum I zero, then I zero e to the I times omega t plus phi I, right? Phi I. Okay, then if I do the integral, right? Well, let's change it back to purple. If I'm integrating this over time, I'm just gonna get, right? So I zero, then because I have the I times omega over here, has to be divided by I omega now, right? I zero divided by I omega, and then times then yeah. So I zero divided by I omega times e to the I omega t plus phi I, right? So omega t plus phi I. And then after that, I divided by c, right? Notice I zero e to I omega t plus phi I, that's just equal to my current as a function of time, right? So this just equals to current divided by I omega c. That's really useful because I can equate it to I times complex impedance, right? I times complex impedance, C. And what does that mean? Well, I just cancel I from both sides, obviously, right? So I'll just get the complex impedance of a capacitor that equals to 1 over I omega times C. That's what we're getting for a complex impedance of a capacitor. And let's look at the phase shift due to this. So again, uh, Now, remember before when I had an inductor, I'm doing like, remember Z of L equals to I omega L, right? And this one is it shifts the V is shifted forward. V shifts V shifts forward by 90 degrees, right? So because now instead of multiplying by I, I'm dividing by I, the so V say this is V of the inductor. So now V of a capacitor shifts back, shift, shift back 90 degrees, right? So if I want to draw, so if I'm looking at this circuit still, I want to draw the current and voltage as a function of time. Let's draw that graph over here. This will be my t-axis. And first, let's say phi I is equal to 0 again. So I'll go, this will be my phi I, right? My phi, oops, phi will look something like this. Your standard cosine function. And on the left-hand side, oops, right? And then on, yeah, and then this will be my I. And this time, the voltage lags by 90 degrees. So uh, I'll draw the voltage with green. So uh, right. So it will be my sine function, right? So oops, right, it will just be sine function. So right, it'll look something like that, right? Uh, this will be my voltage. And then similarly, if I want to draw it on a circle, right? So let's say be my coordinate axis. I'll draw my circle over here, be a unit circle. My current, it will look, for example, what's over there. This will be my current unit vector, I cap. And because VC, right? VC, it's the current, so VC equals to I and then divided by I omega C, right? Because I 1 over I omega C is our complex impedance of a capacitor, right? You're dividing by I, so it shifts it back by 90 degrees. So this will be my complex impedance, or no, that will be my unit vector of the voltage. And you can see it lags by 90 degrees, and let's say they're rotating counterclockwise, and they're both rotating with an omega. So you can think of it as like you can think of the two vectors and they're rotating together by 90 degrees. They're always offset by 90 degrees. The V is always lagging behind by 90 degrees, and they all rotate together with the omega. So yeah, that's just how you do it for a capacitor. Remember the trick we did? Just remember that how we define current, it's dq over dt. So if you want to get the charge, you integrate the current over time. And after that, you can get your complex impedance of a capacitor. Let me draw the C more clearly. So complex impedance of a capacitor is 1 over I omega C, and that causes the voltage to lag behind by 90 degrees. Yeah. Any questions on that? All right. If not, uh, let me give a few more remarks on the complex impedance. So remember, here's like our overall things we got, right? Overall results. So we know the complex impedance of a resistor, that's simply just your resistance. The complex impedance of an inductor, that's equal to I omega L. And the complex impedance of your capacitor, that's equal to 1 over I omega C. And then how are we going to use this? Well, the reason why we use this is because we wanted to define the voltage would equal to the current and then times some complex impedance of some element, right? And then like this really looks similar to Ohm's law, right? Except it's for AC circuits, and then we have the complex impedance here instead of the resistor. Now, what's useful about this is remember how if we had two resistors in parallel or in series, right? Let's say two resistors in series, and then if they have R1 and like R2, we said that the equivalent resistance, so I can replace it by one resistor with some equivalent resistance equal to R1 plus R2, right? R1 plus R2. Now, remember, if I had it in series, so something like this, connected in series, this is R1, this is R2. Then again, I could replace it by one resistor, and I said that the equivalent resistance, right, R equivalent is equal to 1 over 1 over R1 plus 1 over R2, right? This is just like connecting resistors in series and parallel. If you don't remember it, check out the lecture recordings or try to rederive it yourself, right? Now, the cool thing about it is that because Ohm's law and like our complex impedance definition, they're almost the same, except instead of resistance, we have complex impedance, right? That means that if I have, like, for example, if I have an inductor, say I have an inductor and then I got a capacitor, and they're in series, I know each of their complex impedances, right? So let's say I have Z1 over here and Z2 over here. Well, I know that I can replace it with, like, let's call it a box, right? This box, it will have an equivalent complex impedance. Z equivalent will just be like adding two resistors in series. It will just be equal to Z1 plus Z2. And that's really, really convenient. Z1 plus Z2, which will equal to, if you remember, will be equal to I omega L plus 1 over I omega C. And you can do the same thing if you have them in parallel, right? So I have example like that. And maybe I'll even add a resistor here. So let's say I got one inductor, also got a resistor. Say over here, I got a capacitor and they're in parallel. Then I can just replace it by another element that has equivalent complex impedance. And the complex impedances, they just add like if they're in series or parallel, they add just like how they are for resistors, right? The Z equivalent, it will be equal to, okay, uh I have an inductor and a resistor in series, right? And it's in parallel with the capacitor, right? So the Z equivalent would just be 1 over, oh, let me draw that one just to keep space. 1 divided by, okay, first 1 over the 1 over, so 1 over the equivalent or the complex impedance of a capacitor, right? Which I know is also equal to I omega C, 1 over I omega C, right? So it will just be 1 over I omega C, and then plus 1 over the equivalent complex impedance for this section over here, right? So how do I do that? Well, I'm adding the two in series. So I'm just adding the two complex impedances together to go to 1 over R plus I omega L. And that's our overall complex impedance. And you can see it's really convenient because now that you have this as your equivalent complex impedance, you can just say that the voltage across it as a function of time, I can just say like, voltage as a function of time just be equal to the current as a function of time, and then just times the complex impedance, the equivalent complex impedance. It's just really, really convenient because like it's as if you have resistors, but except you have you just call it a complex impedance, and each different element has a different complex impedance. But the really good thing is that if you have like two elements in series, like the complex impedances add like their like two resistors in series, right? And then if they're in parallel, it adds like two resistors in parallel. So that's like a really, really convenient thing about complex impedances that uh that's like a big reason why we like invented complex impedances and why like people study it, right? So uh so basically important takeaway is just remember this is how we define complex impedances for each element, and then how we define the voltage across each element in terms of the current and the complex impedance. And then really, really big thing you should know is that, and it's like really useful, is that the complex impedances, they add like resistors in series or parallel. So if I were you, I really study this. It's really important. And it's really, really useful to know these complex impedances. Yeah. Any questions about this? We're just about running out of time. All right. Yeah, let's want to take a screenshot of this, you can. Or actually it's in the lecture recording. So yeah, we'll post that later. There's just one last slide let's go over. Probably, wait, we already went over this. So yeah, we did this too. Yeah. All right, it's just this one. Solve for the complex impedance Z. Solve the current as a function of time. Since we're running out of time, we'll probably just leave this as homework. But just remember, if you want to do this problem, remember the complex impedance of a capacitor is 1 over I omega C. 1 over I omega C. This is I omega L. And this complex impedance is simply R. And if you want to find the total complex impedance, Z total, because these three are all in series, you can just say it's equal to like just the sum of all of the complex impedances. And then once you have that, you can say the current as a function of time that equals to your voltage, which is given to you over here, right? It's a sinusoidal voltage. So V0 sine omega t, and then divided by your total complex impedance. And that's how you solve this problem. We'll leave it for homework to you for you to like basically wrap your mind around the concepts and also figure out the calculations. But this is overall how you do this problem. So yeah, uh, if you have any last questions, maybe like message us in Discord or right now or send us an email. But otherwise, yeah, important stuff. Just remember your RL, your RLC circuits, also complex impedance, really, really important topic. I know today was a really intensive class, a lot of material. So be sure to review the lecture recording. Um, Make sure to review and do the homework. It'll be really helpful for you, okay? Yeah, so yeah, we're done for today. Have a good day. See you next week, which will be our next week will be our last class. So yeah, see you then.